Welcome everyone to the colloquium. We have Professor Kyeong-Dong Park, who will speak on algebraic moment polytopes of polarized spherical varieties. Let's welcome Professor Park.
I'm going to accept organizer of postec colloquium. It's my honor to give a talk in colloquium. Okay. My title is Algebraic moment polytope. Moment polytope. Polarized spherical variety. Is my outline today talk. I introduce what is the spherical variety. Spherical variety. And I explain the lunar burst theory. Lunar burst theory on colored band. And then I'll define a algebraic moment polytope. Polarized spherical variety, where X is a spherical variety and L is a G-linearized and blind bundle. And lastly, if I have some time, I'll give a application. Classification and case stability of Ornstein-Fano compactification, equivariant compactification of semi-simple algebraic group. Simple algebraic groups. Yeah. So let's define a notion of a spherical variety. Yeah. What is a spherical variety? Let's define a spherical variety. Normal algebraic variety is called normal algebraic variety. Is denoted by X. It kept with an action of reductive algebraic group. Reductive algebraic group G. Is called so-called G variety. For short. Is called spherical if Borel subgroup B, subgroup B, X on X with openness OB, openness BOB with condensed OB. is a definition of spherical variety. Yeah, here in my talk, yeah, G means a reductive algebraic group, and E means a Borel subgroup. Yeah. By definition, Borel subgroup is a maximum connected solvable algebraic subgroup of G. Yeah. So by definition, a Borel subgroup means a maximal connected solvable subgroup. Yeah. So the reason why Borel subgroup is important is that it comes from the Lee-Colchin theorem.
I'm very sorry, it's
Yeah.
subgroup G, maybe.
Oh, yeah. Thank you. Yeah. Thank you so much. G. You're right. Lee-Colchin theorem. Yeah. The Lee-Colchin theorem says that if B is B the representation of solvable algebraic group. V is a representation of solvable algebraic group. Yeah. On non-zero finite dimensional vector space, space V, and V contains a simultaneous eigenvector. Case. Eigenvector for all P. Is called Lee-Colchin theorem. So let's consider. Let's introduce another notion of G-stabilized Rhine bundle. Rhine bundle L to X is called on a G variety. G variety X is called G linearized. If its total space L, has an action of reductive algebraic group G, and such that projection map. The projection map P is a G equilibrium, and the induced map, on fiber in the fiber and subscript x to and subscript gx. Yeah. With a linear map, linear for all g and x in G over X. Such a line bundle is called G linearized line bundle. So it is a G linearized line bundle on G variety X. Then the space of global sections. Yeah. The space of global section has a natural reaction. It's a natural reaction. Natural G module structure. And all the power of G linearized line bundle, yeah, and all power of G linearized bundle are also G linearized line bundle. G linearized line bundle. So let's introduce one more terminology. Yeah. G module. V is called multiplicity free if dimension of G module, the dimension of the space of G homomorphism, G module homomorphism from irreducible G module with the highest weight lambda to given G module is equal to dimension of B semi-invariant vector with the character lambda. The dimension of space of B semi-invariant vector with character lambda is less than or equal to 1 for any dominant integral weight lambda. Integral weight lambda inside monoid of dominant integral weight inside character lattice of maximal torus. Here is a maximal torus of given algebraic variety G, maximal torus of For example, if you consider consider general linear group as a reductive isolate group, GL and C. Then Borel subgroup is a subgroup consisting of upper triangular matrices. The subgroup of upper triangular matrices. Subgroup consisting of triangular matrices. And maximal torus consists of diagonal matrices. Yes. Diagonal matrices. The typical example of reductive isolate group, Borel subgroup, and maximal torus of G. If you have a question or comment, please.
Why were you doing this? Is there like something to do with this sphere?
Yeah. Originally associated the electrically speaking, the origin of terminology comes from harmonic analysis on spherical function. Yeah, but
For GLN, do you understand which irreducibles are multiplicity free, for which lambda that condition is satisfied?
What lambda?
So irreducibles of GLN are indexed by dominant weights lambda, right?
Yeah, it's a irreducible G module
Yeah.
with highest weight lambda.
Yes.
Yeah.
And you gave a definition, which is that it's multiplicity free if that happens. Do you understand?
All dominant weight. G module.
Could you give one example, maybe?
One example. Yeah. I give an example for later. Yeah. Give an example. G linearized 라는 건데. Give an example of G linearized model. Yeah. Give a simple example. 자, okay. Let's consider GL PGL to C times PGL to C, and G acts on the space of 2x2 matrices. G acts on the 2x2 matrix. Exactly speaking, productivization of space of 2x2 matrices with complex entry is isomorphic to three-dimensional complex projective space. Yeah. And let's consider anti-canonical line bundle, because since and canonical line bundle of projective space. AP3 minus 1 is isomorphic to line bundle of degree 4. Yeah. So the space of global section over P3 of anticanonical line bundle is isomorphic to fourth symmetric power of standard representation. It's well-known vector algebraic geometry. So we can decompose of irreducible representation of G. I mean, endomorphism of PGL2 module with the trivial representation and break sum of ends PGLC module with height weight 2 times fundamental weight. And last one is endomorphism of PGL to see 4 times fundamental weight. So multiplicity free G module means we have only one copy of irreducible G module in the decomposition of irreducible G module decomposition.
And here, fundamental rate is the fundamental rate for PGL to C or G.
PGL to C. Here, pi 1 means fundamental weight of PGL to C.
But our original work is based on the G. Original G is like 2 copies of PGL to C.
Yeah.
But right, works well. Okay, thank you.
All right. So, exactly speaking, our P is a 2 copy of maximum torus of PGL to C. Yeah. All right. So you can think of a homogeneous space. Homogeneous space of diagonal G modulo diagonal PGL C portion by, because we will consider only homogeneous space of G2 times G2 modulo diagonal embedding of some semi-special group. We identify a 2 copy of weight lattice of S times S with weight lattice of simple algebraic group. Is there more question?
So in this G, can you so you will give example of this multiplicity free V later, right?
the simplest example is trivially irreducible G module. Yeah, sure. Goes that by sure lemma. V is a irreducible G module with some weight mu. Then if lambda is equal to mu, then the dimension of the multiplicity is just 1, and otherwise the multiplicity is equal to 0. Yeah, this is a simplistic example of multiplicity free. And
I see.
So multiplicity free roughly means the direct sum of irreducible representation without.
yeah. Exactly. Right. Let's move to page. Program characterizing spherical variety that exterior normal quasi-projective G variety. Then the following are equivalent. X is a spherical variety. Spherical. It is X has a open dense B orbit. Yeah, that is X has a open dense B orbit. And second, any invariant rational functions on X is constant. Equivalently, any B semi-invariant rational function in function space of X is uniquely determined by its character or its weight. Up to constant. And the third one is for any G linearized line bundle, L line bundle on G variety X, and the space of global section of a linearized line bundle L on G variety X is a multiplicity free G module. These are three statements all equivalent to the following equivalents. In order to prove the implication from 1 to 2, because X has a Zariski open dense BOB. So any p invariant rational function must be constant. Yeah, simplicity implication. And let's assume the second statement. I mean, assume any b invariant rational function on G variety X is constant, then X has a open B open. This direction. Prove this direction. We recall the Rosenrich theorem. Rosenrich theorem says that B orbits in general position can be separated by invariant function. Invariant rational function. I mean, in other words, there exists a B-stable affine open subset of X such that right. There is a affine B-stable affine affine open subset U in X such that for all different points inside U with different BOB, X is not equal to BY. Then there exists a B invariant rational function. Invariant rational function satisfying Fx is not equal to Fy. In other words, Rosenrich theorem says in state one. So by assumption, any B invariant rational function must be constant. By assumption. We conclude that U must be a just single BOD. Yeah. U must be a single BOD. So this two statement is equivalent statement. will use this theorem. Yeah. Can I use this both? Yeah. And then the other, to prove the implication from 2, 3. Yeah. Suppose L is a G linearized line bundle on G variety X. Yeah. Here L is a G linearized line bundle on X, G variety X. And let's take a two section, S1 and S2 in the space of global section of L. B semi-invariant section. Let S1 and S2 to be semi-invariant, for the eigen section, invariant sections with the same weight, lambda, lambda. Monoid lambda is a dominant integral weight. So which means that B dot S1 is equal to lambda B S1 and B X on S2 is equal to lambda B times S2. Yeah. The semi-invariant condition means implies this equation. Then the rational function S1 over S2 is B invariant because S1 and S2 has the same weight, so we can construct the weight function. So the rational function S1 over S2 is a B invariant rational function. So we assume the second statement because by assumption the space of B invariant rational function is constant function by assumption. So S1 and S2 are proportional. Therefore, the space of global section of G linearized line bundle L is multiplicity free G module. And the last, for the last implication, we need to one more result. Yeah, so called Sumihiro theorem. Sumihiro theorem. Sumihiro theorem says that every normal quasi-projective G variety X yeah can be embedded equivariantly G equivariantly in the projective space of finite dimensional G module. In the projective space of V. Here V is a finite dimensional G module. Finite dimensional G module. This is a Sumihiro theorem. So from the Sumihiro theorem, let's fix embedding, equivariant embedding of G variety. Delta is a fixed G equivariant embedding of projectivization of finite dimensional G module. Yeah, yes, equivariant embedding. And take a pullback line bundle of dual topological line bundle over projective space of PV. Then L is a G equivalent bilinearized line bundle, G and very ample line bundle over G variety X. Yeah, then and is G linearized line bundle. Yeah. And very ample line bundle on X. And so restriction to given G variety X, give a G equivalent epimorphism from symmetric power degree M and dual space of V onto the space of X M tensor power of variable G-linearized variable bundle. And from this injection, embedding, we get a G equivalent epimorphism of a space of global section, a space of global section of m tensor power, m tensor power of O1. Symmetric power of m symmetric power of vector is isomorphic to global space of global section of PV of line bundle OM. Then if you take two, yeah. Okay. Invariant rational function f non-form f invariant rational function on x. Then there exists some degree n, the term n, and polynomial p and q in symmetric and symmetric power of equal such that f is a portion by p and q, p over q, p restriction to x of polynomial x over the restriction of polynomial q. Yeah. Then my claim is that suppose yeah, we can choose polynomial p and q to be p eigenvector. So I explain. So yeah, let's consider B module. Consider B module. Let's denote W. The space of Q prime, yeah, in symmetric M symmetric power of visual, such that there exists a P prime in symmetric M symmetric power of visual, such that P prime, the restriction of P prime is equal to F times Q prime X. Then we can check that the space of Q prime, such a Q prime, is a B module. And is a non-zero finite dimensional B module. Then, yeah, by by the Ricolchin theorem. Ricolchin theorem. 이 마줄 W should contain a non-zero 이 eigenfunction. eigenfunction. The result from the Ricolchin theorem. So our F is b-invariant rational function, and we can take a b eigenfunction q prime. So we obtain a b eigenfunction q prime from this relation. In our situation, we assume the third statement. For any G linear line bundle, the space of global section is multiplicity 3. This means by our assumption, the space of global section and tensor power of G linear variant line bundle L is a multiplicity 3 G module. So restrictions P and Q are proportional. In other words, the same up to constant. Proportional. This means F should be a constant. Anyway, yeah. Graph implication is a result of basic result of Ricolchin theorem. Any question? Anyway, please remember the characterization of sphericality. 3 statements or equivalent statement. So let's move to lunar burst theorem. Lunar burst, Domingo Luna and Pierre burst. Yeah, prove that in 1983. Right. Homogeneous space G mod H here. Spherical homogeneous space. Then the map associating spherical embedding of G mod H into G variety X. The map from the map which associate spherical embedding of spherical homogeneous space into G variety to strictly convex colored fan. Fan denoted by Fx. Yeah, colored fan is a finite collection of colored cones. Collection of colored cones. And colored cone is a pair of cone and set of finite set of some divisor, so-called color. Anyway, color band is a very combinatorial object obtained from the geometry of spherical variety X. Very combinatorial object similar to toric variety. The difference is only we need to consider color. Very similar combinatorial object. Toric variety.
G and H are fixed.
Yeah. We fix
Then in
spherical homogeneous.
the left side we have some data from G and H, but the right side does not have any.
Yeah. Associate to associate
G and H.
colored band. Spherical homogeneous. But H. So Luna was to prove that this map is a bijection up to between G isomorphism class of spherical variety, between G isomorphism class of spherical embedding of G mod H, and strictly convex colored band associated to spherical homogeneous G mod H. So proved by and Thierry Frost. So
Is there an example that you can give, like, or is that too complicated even?
Right. Let's try. In my opinion, the simplest example of non-Toric spherical variety, spherical homogeneous space. I think, let's consider simple example. Let's consider SL to C modulo maximal cross T. And consider the action of action of E times P on SL to C. I mean, EX on the left, PX on the right. Yeah. Yeah. And in provide matrix S, equal 1 minus 1, 0. And U, the unipotent element, so 1, 1, 1, 0, 1. Then we can compose SL2C is composed into 3 p orbit to 3 orbit S B B S and P S U T. Yeah. Hopefully you can check that. So SL2 has a 3 B orbit. Here, B is a Borel subgroup of SL2C. I mean, the subgroup of upper triangular matrices. Then SL2 modulo T has a 3 B orbit. Yeah. B. It's B orbit. Give a open B orbit. Yeah. modulo T is the open B orbit. 2-dimension open orbit. And have a two divisor. Yeah. Two divisor. Let's denote D plus and D minus divisor. Definitely, yeah, B stable divisor. So we have a 3 B orbit. One is a open B orbit, and the other 2 orbit is a divisor, 4-dimension 1 orbit. Yeah. Here, E plus the E modulo T, and divisor. Yeah. Let's consider E is a subgroup of upper triangular matrices. So D plus is a divisor of A21. Yeah. Divisor of A21. Right? Right? Yeah. Here A11, A12, A21, A22 is a corresponding entry. Yeah, corresponding entry. So the fourth B-stable divisor is given by A21, and the other B-stable divisor D minus minus is yes, Yes. Yeah. If you multiply by S on the right, you can change switch the entry. So this divisor given by you can compute easily that divisor of A to 2. In the universal theory, these two B-stable divisor called color. So by definition, color is a B-stable, but not G-stable divisor in spherical space image H. Is a definition of color. That's theory of universe. So our colored cone is generated by the image of color map, and the finite G invariant valuation. Definition of colored cone, and delta means subset of set of colors of given spherical homogeneous space Gmat H. So question?
Yes, what it exactly is a cone here?
Cone is
It's a
two-dimensional cone is something like that. Yeah. Cone. Colored cone C. Colored cone C is generated by some G invariant valuation and the color map, image of color map. Color map yeah, some color. Yeah.
Could I think of this cone as living in the weight lattice or just
Yeah.
independent of?
Yeah. Inside the dual weight lattice.
Oh, okay.
Yeah. I need to too many terminology.
Okay.
M is a spherical weight lattice. The lattice of character.
Yes, yeah.
Character of B semi-invariant rational functions. Denoted by M. The dual, colored cone lives in dual weight lattice. Enough time. I don't have enough time. Yeah, let's move to let's move to moment moment polytope. Yeah. Yeah. As for LBR G-linearized amplifying bundle. On G variety, spherical G variety, spherical G variety X. Then the algebraic moment polytope. Moment polytope. Pair of polarized spherical variety. Yeah, is defined as the closure of union k times 1 over k times delta k inside character lattice of maximal torus tensor R. Closure here, k runs all natural number. Yeah. Here, delta k is the finite set consisting of dominant weight lambda such that the space of global section of K tensor power of given amplifying bundle, linearized amplifying bundle, is a composition of irreducible G module with the highest weight lambda. Delta K. This is the meaning of the delta K, and by definition, algebraic moment polytope is the closure of the union scaled by 1 over k times delta k. Yeah. But by the multiplicity free property of spherical G variety, the algebraic moment polytope encode the structure of representation of G in the space of multisections of tensor power of amplifying bundle L. Like that. Definition of algebraic moment polytope. Let's give a very basic example. Let's give an example. Algebraic moment polytope. Simplicity, I think simplicity example. As before. Yeah. Before giving a example, let's take one more theorem. Yeah. Note that the notion of algebraic moment polytope was introduced by Michel Bouillon in 80s. Michel Bouillon give a
Maybe
Time is little. I mean,
then can we finish in like 10 minutes or
Oh.
15 at most? We're a bit late on time.
yeah. I have a
10 minutes, is that okay? Or
yeah. Okay.
15 at most, maybe?
Yeah.
Or 10, it's better.
I'm very sorry.
Uh,
이거 theorem proven by Michel Bouillon. Yeah. If X is a Fano spherical variety, I mean, the anti-canonical line bundle of X is ample line bundle on a spherical variety. Of spherical variety of spherical homogeneous space. H. Then we can represent the B stable Bayes divisor minus Kx is equal to sum of I di K plus B. Here di is a color and Bj is a B stable divisor. Then the algebra moment polytope of anti-canonical line bundle is a translation of some polytope. Here, psi is a B weight of section of anti-canonical line bundle, and the polytope QX is a convex cone, convex hull of the set of rho mi over mi k union rho so the definition of algebraic moment curve is very complicated, so not so easily computed. Michel Bouillon give a computational method. It's just a translation of some polytope. So we can compute the algebraic moment polytope. I step.
Let's take our speaker. There any questions or comments?
Is there any relation between algebraic moment polytope and toric variety? Because in simplex geometry, Gyeongsang polytope and toric manifold is it's the same object, but algebraic moment polytope.
Well, enough time. I would like to explain the relation between algebraic moment polytope and common polytope. Yeah. As you know, you can think of here K is a compact connected real group and M is a symplectic manifold. So we can think of a Hamiltonian K action on simplex manifold. So we can obtain a common polytope. So yeah. So common polytope. Yeah. I did not. Yeah. Briefly explain. Yeah. So the algebraic polytope is a intersection of common polytope and positive Y chamber. Positive Y chamber T plus. Briefly speaking, yeah. Algebraic moment polytope is an intersection of common polytope given by moment image of moment map given by Hamiltonian K action on symplectic manifold. Intersection positive by chamber. So,
Any other questions or comments?
So this polytope is related to K stability of this
yeah.
spherical variety.
Okay, so many people, yeah, from the many results proven by the case stability of Fano spherical variety. Equivariant case stable if and only if the very center of moment polytope of anticanonical line bundle with respect to Twist-Matrix common measure inside the some cone. Yes, some cone. Yeah. From this, by this result, if you want to check the equivariant K stability or existence of Caroline metric, we need to check the very center of moment polytope of anti-canonical line bundle with respect to Weisstomat's Heckman measure. Thank you for your question.
Thank you.
Any other questions or comments? So in your theorem, like you're trying to say that you have some combinatorial understanding, right?
Yeah, you're right.
Is this, but this seems to be a bit hard in general. Are there any examples, like if you specialize X, where you can get something more manageable, like where the combinatorial becomes easier? So for example, if X is like symmetric or something like this?
You mean symmetric variety?
Yes.
Yeah. Metric variety is more easy to deal with, because we have a classification of involutions,
Okay.
defining symmetric
Okay.
homogeneous states.
So in that case, if I give you a symmetric variety, can you write down everything combinatorially explicitly? Okay. Okay, any more questions? No. Okay, so thank our speaker.
Yeah.